Welcome, exceptional engineers. This is Prof G, and I hope that you pin this video as a favorite because we're going to learn how to identify pins on a CircuitPython board. We're going to run a small script that you can use on any CircuitPython board to find out all of the names, including aliases, for a given pin. Then we'll compare the results of running the program on an Arduino Nano RP2040 Connect and 3 Adafruit boards, the Feather RP2040, the QT Py RP2040, and a Circuit Playground Bluefruit. And we'll see how this output can help us understand what we can do with each of these boards and how to access their pins and features in CircuitPython. We'll also take a first look at pinout diagrams so we can understand pin locations and their functions. We'll describe some key terms and concepts, and we'll offer tips on board care and safety. And armed with this knowledge, we'll hook up NeoPixel strips to 2 boards with different pin configurations. We'll use the Arduino Nano RP2040 and the QT Py RP2040, and we'll learn to take the NeoPixel goodness that we learned in earlier videos with the Circuit Playground and apply this to get things flashing on boards with different pin configurations. We'll also get our first look at using a breadboard, and I'll demonstrate IC hooks that can be useful if you have a board without any headers. So this is a bit longer video, but after we're done, you should feel comfortable taking CircuitPython code examples and project code and modifying this for whatever board you happen to be working with. So let's pin down these concepts and light things up with more big learning. Now, if you look at the various boards, you can see that the pinholes usually have names silkscreened directly near them. Now, sometimes they're easy to read, sometimes they're super tiny and not in very convenient places. Unfortunately, the names on this Arduino board are underneath the board, which makes it tough when you're using a breadboard. And tiny is not good for someone like me. I have bad eyesight, so bad that I can't drive a car. But every vendor has a pinout diagram that you can search for and find online. When I work with this board, I usually leave the diagram up in my browser so that I can quickly reference where the pins are. But another challenge is that even when you see names, there are often multiple names or aliases for each pin. And you'll definitely want to know which names and objects apply to your pins. So we're going to use a handy CircuitPython program that you can run on any board with CircuitPython installed, and it'll output a row for each pin along with all of the names and aliases that can be used for that pin. Now, rather than typing it in, I'm going to grab the code from an Adafruit page. I'm going to search online for Adafruit CircuitPython pin map script, and I'm going to head to this page, scroll, and find the short script labeled CircuitPython Essentials pin map script. Click copy code, head to Moo, paste in our code, make sure your CircuitPython board is configured and plugged in. I've got my Arduino Nano RP2040 Connect plugged in when I'm running this. Save as code.py, then open the serial monitor, and we see the output. Your output will look different if you're using a different board, and to give you an idea of how output will vary, here is the output from this script compared across 4 different boards, including the Feather RP2040, the QT Py RP2040, and the Circuit Playground Bluefruit. And you'll see more entries for boards that have more pins and built-in capabilities. Not surprisingly, the tiny QT Py has the smallest output, so feel free to look at your specific board. Since I'm using the Arduino Nano RP2040 Connect, I'll use this board for my explanations here. And I'll point out that in an earlier video, we ran a short script to blink the LED light that's built into the board. And when we did that, we used board.led to refer to the built-in LED. Well, we see here that LED can also be referred to as board.d13 or even board.sck because they're all on the same line. Now, it's best to code using the name LED when we want to access the LED light. You want to make sure that your code is easier to read. But just to show you, I can run the blink code and change the name LED to D13, save and run this code. I get the same results. Now, just to stop the blinking, I'm going to cut out the code, resave the code as an empty code.py file, and then I'll paste the code back. I'll change D13 to SCK, save it, and it blinks again. So board.d13 and board.sck do the same thing as board.led on this particular board. And by the way, SCK stands for serial clock. We're not going to be working with that concept in the next few videos, so we'll table a discussion for now. But do be aware that if you use this board, if we look at the pin diagram, there is also a physical D13 pin. So if you plan to use the built-in LED light, you should avoid using pin D13 or vice versa. Now, if we compare the output across other boards, we see that the Feather board's LED can also be called a D13. We see there's no LED on the QT Py, and for the Circuit Playground Bluefruit, the LED can also be called a D13 or even just L. Now, since we started looking at the pinout diagrams, let's keep looking. And again, you can pull up the pinout diagram for your board. Just search for it online. Sometimes an image search will take you right to the image you want. I'm going to continue to look at the Arduino Nano RP2040 Connect as my reference, and first let's look at the ground pins. Now we almost always use ground pins when connecting devices to our boards. This board has 2 ground pins, either one will work, and one thing that's useful on this particular board, even though the diagram doesn't show you, if you look at the actual board, the ground pins are highlighted in white, so they're easy to find. Also know that you can share ground pins across multiple devices, meaning that if you want to use multiple devices or sensors on your board, wires coming from the different devices can share the same ground pin if they need to. Now, devices also need power. Most smaller microcontrollers default to 3.3 volt power. Now, larger or older boards may have 5 volt power, and some boards have pins for both 3.3 volt or 5 volt power, so be careful that you're using the right power pin for any component. And you can search online for a component specs or a data sheet if you're unsure of the power requirements and limitations for a component that you're using. And even though there's a 5 volt power pin on this board, you need to solder a jumper to get this to work, and we won't be doing that in this tutorial. Now, we'll usually rely on 3.3 volt power for things that we connect to the board. This is especially important if working with some components like our potentiometer. That's this knob-like component that we used in earlier videos. If we tried to connect our potentiometer to a higher power source like the VIN, we'd actually get inaccurate readings if we dialed to the high end of the scale. Now, I just mentioned VIN. What is that? Well, VIN stands for voltage input. That's another power pin. VIN accesses the input voltage from power that comes from the USB, as well as any external power source that we might have hooked up. Now, if your power input is higher than 3.3 volts, you should have access to that extra juice. You could also supply extra voltage through this pin, but I'm not planning on doing that in any of our tutorials. Now, as mentioned, you don't want to provide more power than a component can handle. That might even damage some components. But we often do have higher power component needs where VIN makes sense, such as the multi-light NeoPixel strips and strands that we're using, or the servo motors. So when we use those components, we'll plug the power pin into VIN. And like the ground pin, it's okay for components to share a board's power pins too, but know that it is possible to use more power than is supplied by a board. Hook up too many NeoPixel lights or too many motors to a board, for example, and your lights might dim, or your motors might not even run. We won't be exceeding any limits in our tutorial videos, though. Now, we've also got lots of digital pins on this board to use for digital input and output. These pins are labeled with D followed by a number on this particular board, although that could vary by board. And if you're following along with our previous CircuitPython school videos, there were lots of lessons where we used digital I/O libraries, including working with buttons. Those are digital inputs. And examples of digital outputs also include when we worked with sound, sending audio to the speaker, working with servos, where we sent out a signal to control a motor, and even the blink script that we just wrote. Now, you'll also notice on this diagram that the label GPIO is included on those pins. Now, GPIO stands for General Purpose Input and Output, and while we don't use this in our CircuitPython code, we don't see GPIO on the output for any of the boards we're looking at in our pin map scripts. GPIO often appears in schematic diagrams, and when you see that, it's safe to assume that you're looking at digital pins. Now, when working with digital input and output, if you're using this Arduino board or a similar board, I recommend focusing on the ones over here that are labeled D, D2 through D10, and they don't have any other names. And I'd say if you're using digital input and output, use these pins until you run out of digital pins, because the pins over here can be used as digital I/O as well as analog I/O. They can be used as both, but you might want analog I/O in your project, so keeping these pins over here with an A in the name keeps them in reserve in case you think that you might need analog I/O at some point. Also know that even though a name shows up in a pinout diagram, that does not mean that it's available in CircuitPython. You see how in the diagram here, A0 through A5 are also labeled as D14 through D19? Well, if we go over and take a look at the pin mode script output, the pins A0 through A3 don't have any alias names. So if you want to use these pins on this particular board, you can only use the names A0 through A3. Now, speaking of analog I/O, remember digital I/O has 2 states, on or off, 1 or 0, true or false. But when we use analog I/O, we have a range of results. So as an example, we used analog I/O when we work with our potentiometer knob, and you could turn that knob and get a return value which ranged from 0 to 65,520. So if you're working with analog I/O on this particular board, you should select one of the pins that has an A in their name. Now, in most boards, analog pins can be used for digital pins too. So if you needed to, you could use these dual analog digital pins for digital use, even though the boards are board.A0 through board.A3. In fact, when we worked with the Circuit Playground in earlier videos, all of those pins were labeled with A's, so the letter in the label name doesn't limit a pin's use. Just check with online documentation to see if the pin that you're using is digital only or digital and analog. On this particular Arduino board, the D pins are your digital pins, the A pins are analog and digital. Now, another thing to note for this board, the Arduino Nano RP2040 Connect, do not use A6 or A7. So even though these pins are in the pinout diagram, they are not in the pin map script output, and these are not accessible in CircuitPython. That's the kind of thing that's also made explicit in the Learn Guide. So again, if you use a new board for the first time, always read the Learn Guide. Now, another thing we're going to be working with is wiring up devices that communicate with our board using a communication mechanism called I2C. Now, in an earlier video, we mentioned that I2C is the communication scheme used in what Adafruit calls the STEMMA-QT port. SparkFun calls this the quick connection. This is a really handy connection to use because it takes the 4 wires used in I2C and it allows you to plug them into a single port, like we see here with this cable that connects the temperature sensor into the QT Py. Now, I2C has 4 wires: power, which is usually red, ground, which is usually black, SDA, which is data, and that's usually blue, and SCL, or clock, which is usually yellow. Now, if your board has a STEMMA-QT connector, you can see how handy this is, but the Arduino Nano RP2040 Connect board doesn't have a built-in STEMMA-QT port, but we can wire one up using a cable like this that has 4 wires with pins on them on one end and STEMMA-QT connections on the other. So to do that, power or red will go to 3.3 volt, ground or black will go to any ground pin. So where should we plug in these other 2 cables? Well, if we look at the pin map output, we can see board.sda is alias to board.a4 on this board, so we should plug the blue wire into A4, and board.scl, which is the yellow clock wire, should be plugged into board.a5. And we'll show you how to do that using a breadboard in the next video when we work with STEMMA-QT. By the way, if you wanted to add a STEMMA-QT port to a Circuit Playground Bluefruit, you could also do that. If we look at the pin map script for that board, we see that SCL is A4 and SDA is A5. They're actually flipped from where they are in the Arduino board, but you can use alligator clips or even solder the connections on the Circuit Playground Bluefruit, and you'd have a STEMMA-QT connection there as well. Now, regardless of whether you wire up a STEMMA-QT port or you've got one built in, we can simply refer to an I2C object in our code like this. If we give it the name I2C, we just set it equal to board, dot, and in capital letters, I2C, open and close parens. Now, if we keep looking at this output from the pin map script, we can also see that there are other things that are board specific. So for example, on the Arduino board that I'm using, we see some things referring to the built-in microphone. On these other 3 boards, we have NeoPixel lights, but there's not a NeoPixel on the Arduino. We have LED objects on all boards except for the QT Py. And in an earlier lesson, we also showed how code would crash on a QT Py if we tried to refer to a non-existent LED object. Also, if you look at the Circuit Playground Bluefruit, you see all sorts of extra objects: the light sensor, the temperature sensor, accelerometer, audio for the built-in speaker, buttons, switches, the microphone. Now, not to overwhelm you with too much information, but I thought that I'd mention 2 other terms that you might come across when you're reading Learn Guides, but we're not going to be using these terms in our next few lessons. Now, while I2C is the most popular communication mechanism between boards and devices, it's what's used inside of STEMMA-QT, there are other protocols as well. These include SPI or SPI, which stands for Serial Peripheral Interface. You might use SPI for things that need to be sent large amounts of data, like this TFT color display. SPI also involves more wiring. Now, some boards and diagrams label pins reserved or recommended for SPI use. These would include MOSI or MISO on older boards. Those are outdated terms, but you'll still see them around a lot. They're being replaced by newer terms, COPI and CPO, which stand for Controller Out Peripheral In and Controller In Peripheral Out, respectively. There's also another mechanism called UART, which is a type of serial communication. This mechanism uses the RX and TX pins that you see here. You're likely to see these if you're connecting a GPS device, a MIDI device for music. UART is also used in certain biometric devices like fingerprint scanners, as well as peripherals like thermal printers. We're not using any of those in our lessons, though. You might see this term show up in Bluetooth code, even though we don't deal with any wiring when we work with Bluetooth. So with our newfound understanding of our board, the pins we can use, and some of the key terms we'll encounter in Learn Guides, let's wire up some NeoPixel lights. Now, the same wiring approach will work with either NeoPixel light strips or strands, because they both have the same 3 wires. Remember from our earlier video, NeoPixel lights have 3 wires for power, usually red, ground, usually black, and data. Here, that's the white wire, and I'll show you a few ways we can connect this to different boards. Now here, for my Arduino Nano RP2040 Connect, this board has breadboard-friendly header pins. So I'm going to plug this board into the breadboard. That's this little plastic rectangle here, and the breadboard is going to help me easily set up connections between the pins on my board and the wires in my devices. Now I'm going to plug the microcontroller in like this. The header pins soldered to the board fit into the holes. Put your USB port to the side of the board so that your USB cable doesn't go over the breadboard. And notice when I plug my board in, these legs, the pins on the board, are straddling this gap here, the center line, which is sometimes called the ravine. And a quick bit about breadboards, with the orientation that you're seeing on screen, these vertical columns are all connected. All pins top to bottom act as if there's a wire flowing between them. That's because if we were to take the plastic off the top of the board, we would see that there's a piece of metal that connects all of these pins. Now there's not a connection across the ravine, so these column connections stop here. And now that we know how a breadboard works, I'm going to wire up the NeoPixel strip to my microcontroller like this. Since this NeoPixel strip has alligator clips on it, I'm just going to clip each of these alligator clips to a jumper wire with pins on both ends. Then I'm going to push the other end of the jumper wire pin into the right breadboard hole. So I'll put power to VIN, ground to one of the GND pins, and in this case I'm going to wire data to D7, and just make sure that we remember to use D7 in our code. Now since the pin names aren't on the top of the Arduino board, I'll double check my diagram to make sure that I'm using the right pins. So in this orientation, VIN is the first pin in the top left, ground is right next to it, and on the board the ground should be highlighted in white, which is very handy, and D7 is the sixth pin from the right on the bottom row, and it's lined up with the left side of this middle chip. Now it's always harder to see on the video, so definitely consult the diagram I provided when wiring your own things up, but to show you, my power wire goes into the same column as the VIN on the microcontroller. That's this first pin in the upper left, and any of the holes in this column will do. Then the pin next to that is highlighted in white, that's ground, so I'll plug my black jumper wire into that column. Always take extra time to make sure that you're never going to plug power and ground into the same column. And finally, my white signal wire is going to go into D7. That should be this column right here, and you can count over from the right just to make sure that you're getting the right column. And with this, our wiring should be correct. And before we plug our board into our USB cable, now's a good time to review some board care and safety tips. So first, the metal parts of wires in your project should never touch. If that happens while the board is powered on, the board could short out. Now, if that happens, it's unlikely to damage your board, although that is possible. So you definitely want to make sure the metal parts of the wires are not touching. But if your wires do touch and you get a short, your code will definitely stop running and your board will probably disconnect from Moo and your computer. Now, if your board does short out, and that happens to all of us, you can just unplug and replug your board back in. That will usually work. Sometimes you have to press the reset button to reboot CircuitPython. You may have to resave any unsaved work from Moo, and in rare cases, when working with some boards, a short has caused me to lose files that were saved to the board. So if you suddenly start to get errors suggesting, for example, that you don't have the libraries that you're trying to import, then double check your LIB folder and re-import any files that might have gotten deleted. And if you're still having problems, consult any troubleshooting sections of the Learn Guides, and you can ask for help in Adafruit forums or on Discord. Now in my connection here, my alligator clips have exposed metal, and it's possible that I might accidentally bump the wires and cause a short. You can probably just spread these wires apart so that they don't touch, as long as you don't move your project around, but if you're uncoordinated like I am, you can always wrap the ends of the wires in tape if you need to. The covers on the ends of alligator clips can also help keep the metal parts from touching. It also makes sense to be careful when you're handling boards. There could be issues with static electricity, although again the boards are pretty resilient, but remember you also conduct electricity. So if your fingers touch multiple active pads on the board, especially if they touch power to ground, you might also create a short. So just handle boards carefully, and if things are plugged in and you're moving them around, try to make sure that you're not touching multiple pads at once. Now another very important safety tip, you want to make sure that you're never plugging your ground wire and your power wire into the same pin. And if you plug your ground wire into a power pin and it's powered, you could see the blue smoke monster. You certainly don't want to damage your board or cause a fire, so be extra careful to make sure that you don't plug ground into a powered power port. And remember, power comes out of 3.3 volt, 5 volt, or VIN pins. Also make sure that you don't plug your data wire into any of your power wires by accident. Never get your boards wet. I don't recommend that you carry your electronics around in your pockets too, but always check your pockets before you do the wash. And it's definitely a good idea to unplug your board from USB or power when you're doing wiring, double check your breadboard connections, and then plug things back in. Now don't be afraid to work with electronics, but definitely keep these tips in mind and pay close attention when wiring things up. So now that I've got my NeoPixel strip wired up to my breadboard, I can plug my microcontroller into the USB port, and I can write a small NeoPixel strip test program. Now you can also save your pin map script if you want to, but now you know where to find that online anytime you need it. And just to test things out, I'm going to write a simple program to light up all of the lights on the strip one by one, then turn them all off and restart. So I'm going to replace the code.py file, it's saved to my board, with this program to test the NeoPixel strip by flashing one light at a time. I'm going to assume everyone watching this has gone through the CircuitPython school video on working with NeoPixel strips, so you'll understand this code, but if not, feel free to go back and review that. I'm going to import board, time, and NeoPixel. Then I'm going to set up a couple of variables, strip_num_of_lights, and I'll set that equal to 30 because there are 30 lights in my NeoPixel strip. Strip_pin, I'm going to set that equal to board.d7. Why d7? Because that's the pin we plugged our NeoPixels data wire into. If you used a different pin, make sure you refer to that pin's name here. Then I'll set up my NeoPixel strip. I'll just call that strip, and I'll set it equal to NeoPixel.N-Neo, capital P pixel, and in parentheses, strip_pin, comma, strip num of light, comma, brightness equals 0.5, comma, auto_right equals true. Then in my while true loop, make sure you have your colon at the end, I'm going to put in a for loop for I in range, and that's going to be strip number of lights, colon, and then inside that, I'm just going to say strip, which is my light strip, in brackets I. This refers to an individual light. I'm going through all the lights in the strip. And I'll set that equal to, in parentheses, 0, 0, 255. These are my RGB colors, and 255 is full on blue. Then I'll pause for 1/10 of a second by saying time.sleep and in parentheses 0.1. I'll repeat this loop for all 30 lights numbered 0 through 29. Then when I've gone through all of those, my loop is done. I'll outdent, I'll say strip.fill, and in double parentheses 0, 0, 0, close double parentheses, that's going to turn off all the lights in my strip, and that's it. After I hit this line, then I start everything over again from the top of the while true loop. So now we can open up our serial monitor. I'll resave this code. We don't have any errors, and look at that. Our lights are flashing, everything's working perfectly. We've just breadboarded with an Arduino and used CircuitPython to light up a NeoPixel strip. Good work, coder! Now just to demonstrate how we can work with different boards, here's a QT Py RP2040, and while the Arduino I was using has headers so I can easily plug this into a breadboard, this QT Py does not. Now I could solder headers onto this board, but sometimes you don't want to do that. You might just want to test out a circuit before soldering the wires directly on the board. Well, one alternative is to use these IC hooks. Now I've got alligator clips to the NeoPixel attached to a jumper wire, and the other end of the jumper wire is in a socket that's attached to this IC hook. And if I pull down on these little handles, you can see that there's a little hook that opens up. I can clamp this directly into the pinholes on my board. This will create a continuous connection without any soldering and without needing headers or a breadboard. So I'm going to hook ground to ground, and although I had previously hooked my NeoPixel to pin D7 on the Arduino, there's no D7 on the QT Py board. So I'm going to clip it to pin A1 instead. I'm going to hook power to 3.3 volts since there's no VIN or VIN on the QT Py. So here's a closer look. Signal to A1, power to 3 volt, and ground to ground. And I'll return to Moo and I'll modify my code so that strip_pin now refers to board.A1 instead of D7. Then save, and we usually have LabCat Admiral Grace in here. This is the other LabCat, Tabitha. And would you look at that? CircuitPython code with only one line modification running on a completely different board. So now you know how to work with different boards even though they might have different pins and different configurations. So we had lots of big learning in this video. We learned how to use the pin map script to identify pins, objects, and their aliases for a given board. We learned how to read and interpret the output of this script across multiple boards. We got our first look at pinout diagrams. We covered key terms I2C, SPI, and UART. We gave some important board care and safety tips. We had our first introduction to breadboards. And we learned to hook up boards with differing pin configurations, modify the code, and get a NeoPixel strip flashing on these boards despite these differences. You should now not only be feeling like a programmer, but also like an engineer. Keep at it, skilled one. There's more goodness to come.